Section 3.5 problems. Find the domain of the function x divided by x squared minus 25. Okay, this one was done in the PowerPoint slide, so what we'll do is a new problem 1. So a new problem 1, let's do the function g of x is equal to 3x squared divided by x minus 5 times x plus 4. And we want to know domain. Okay, to get the domain of the function, only the denominator is important. Take the denominator, set it equal to 0, solve the equation for x. So by doing that, we get x minus 5 is 0, so x would be equal to 5. That's one value we have to exclude. And x plus 4 is 0, so x equals negative 4. That's another value we have to exclude. So all values except these two. You could write that in interval notation if you want. What I do first is show the values I cannot use those, but I can use everything else. So now write the interval notation. So that would be negative infinity to negative 4, union negative 4 to 5, union 5 to infinity. So there's the interval notation description of the domain. Let's take a look at problem 2. Find the domain of x plus 5 divided by x squared plus 25. Okay, so to find the domain, we take the denominator, x squared plus 25, set it equal to 0, and we will not get any values of x, because by taking the 25 over to the right side and attempting to solve for x, we have to take the square root. By doing that, we have a square root of a negative number, so we have no real solution there. So there's no values of x which we need to exclude. So the domain will be all real numbers from negative infinity to plus infinity. There's no value that you can't use even though we have a rational function. That happens sometimes. True or false? Problem 2. The notation x arrow a with a plus sign means that the values of x are increasing without bound. No, that's not what it means. If x is increasing without bound, then x is approaching infinity, or x is approaching negative infinity. That would be increasing or decreasing without bound. Here, x is approaching a fixed number, as I illustrated before in the PowerPoint slides. Problem 3. Find the vertical asymptote. G of x equals x minus 1 divided by x squared minus 1. Okay. We want vertical asymptotes. So g of x is x minus 1 divided by x squared minus 1. Okay. We want the vertical asymptotes. You have to first remove any common factors and fully factor the top and the bottom. The bottom we can factor as a difference of two squares. See, the domain of this function is all x except plus and minus 1. Those are the two values that make the bottom 0. But if you want the vertical asymptote, you have to first remove any common factors. And we do have a common factor to remove, and that yields this more simplified function for g of x. Now, where is this function not defined? So if x is negative 1, that's no good. X can't be negative 1. So that's where we have our vertical asymptote located, only at negative 1. Let's go on to problem number 4. Okay, this problem was done in the PowerPoint slide. Find the horizontal asymptotes for this function. So let's do a different version of this one. So let's do a new problem 4. Let's take f of x to be, let's say, the rational function 3x squared plus x minus 4 divided by 2x squared minus 5x. There's a different variation from what we've already had. And we want to find the horizontal asymptotes. Okay, so to get the horizontal asymptotes, take the highest degree term in the top, so scan the entire top. The highest degree term is 3x squared. Take the highest degree term in the bottom, scan the whole thing, that's 2x squared. Divide them, and you get 3 halves. Therefore, y equal 3 halves will be your horizontal asymptote. Problem 5. Graph the rational function. Okay, this one was done in the PowerPoint slide, so let's do a variation of number 5 here. Let's take the function to be x minus 2 divided by x plus 2. Okay. So we need to graph the function. So, number of things we have to get. Y-intercept, x-intercept, vertical asymptotes, horizontal asymptotes, at least, and maybe extra points. Maybe. And we could test for symmetry. Let's get the y-intercept first. So the y-intercept is when x is equal to 0. 0 minus 2 divided by 0 plus 2 will be negative 1. So the y-intercept is at 0, negative 1. So it crosses the y-axis there. Let's get the x-intercept. X-intercept are where the function is equal to 0. So where is x minus 2 divided by x plus 2 equal to 0? The only way a fraction can be 0 is if the numerator is 0, and that yields x equals 2. So we have an x-intercept at 2, 0. And I'm going to visually tell myself the important results that I have found here so I can find it on my messy paper. Now we need to look at vertical asymptotes. Okay. Vertical asymptotes, remember we have to simplify the function if at all possible. No further factorization here is possible, no common factors to remove. So to get the vertical asymptotes, we simply take where is the denominator equal to 0. And that would be when x is equal to negative 2. So we have a vertical asymptote at the value x equals negative 2. The graph will never cross that vertical line. Okay? Let's get the horizontal asymptotes. Okay, the horizontal asymptotes, we have to look at the function again, take the highest degree term top and bottom, and that's just x on the top and x on the bottom. So when you try to find the horizontal asymptotes, highest degree term in the top divided by highest degree term in the bottom, you get 1. Therefore, y equals 1 will be your horizontal asymptote. Okay. What I'm going to do before I test for symmetry or plot any additional points is I'm going to start drawing the graph to see what I have, and that will then tell me what I need. So let's see. We've got x equals negative 2 is a vertical asymptote. So there's negative 2. So a vertical asymptote here. Okay, so there's the y-axis, x-axis. and we have a horizontal asymptote at 1. So here, horizontal asymptote. And it's already visually confusing because we have the y-axis and we have the x-axis, and we also have these other two horizontal and vertical lines as well. So that takes care of these two items. Now the x-intercept is at 2, 0, 1, 2. So there is a point on the graph. And the y-intercept is at 0, negative 1. So there's negative 1 right in there. Okay. Is that everything? Y-intercept, x-intercept, horizontal and vertical asymptotes? Yes. Okay. So I'm fairly certain what's going to happen. The function is generally trapped by its horizontal and vertical asymptotes. My guess is that it's going to be a nice smooth arc right in here like that. How do you know that? Well, we could plot, say, negative 1 and see if we get a value right here. We could do that right off to the side here. F of negative 1 will be negative 1 minus 2 over negative 1 plus 2. So that'll be negative 3 over 1. So that's the coordinate negative 1, negative 3. Yes, that's really good. Negative 1, negative 3 would put us right down there, wouldn't it? There's negative 1, and that's negative 1 for the y, so negative 3 would be lower. So that makes some sense. Okay. We could also try, say, 3 to verify that we get a point up here. So now you see what points might be useful to plot. Over here, we don't know anything. And the function is probably either trapped up here in the corner between the vertical and horizontal asymptote, or it's probably trapped down here. So how do you know? Well, that's where some point plotting is a smart thing to do. So let's take points. Let's do f of negative 3. So that would be negative 3 minus 2 over negative 3 plus 2, or negative 5 over negative 1, or 5. So that's negative 3, 5. Well, negative 3, 5, 5's way up here somewhere. That puts a point up there. Just based on that one point, I'm assuming, see, I have a lot of practice and background, and the more you do, the more you will understand. Probably that is what the other piece of the function looks like. How do you know that? Well, plot another point. Come over here. Maybe negative 5. Maybe try that one. And let's see if we get a value slightly above 1. If we get a value less than 1, then it's crossing the horizontal asymptote. It can do that, but then it has to come back up to it, since that's the behavior of graphs near horizontal asymptotes. These do take work. They do take practice. So let's plot one more point. Let's say f of negative 5. So negative 5 minus 2 divided by negative 5 plus 2, negative 7 divided by negative 3 is positive 7/3. That's a little more than 2. Aha. That's above the horizontal asymptote. So again, it's up here as we thought. If you're not sure, that's why, again, you're plotting the points, is to help guide the curve through points in mysterious places where you don't have any data. Okay? And you can see here we have no symmetry with the y-axis or the origin, so it's probably good that we didn't do that from the beginning. Okay, let's see what else we have to do. Graph another rational function. Okay. F of x here, x to the 4th divided by x squared plus 2. X to the 4th divided by x squared plus 2. Okay. So let's get the y-intercept. F of 0 is 0 divided by 0 plus 2. So that'll be 0, which means that the origin is part of the graph. We can attempt to get the x-intercept by setting the function itself to 0. The only way the fraction can be 0 is if the numerator is 0. And by solving that, all we get is x equals 0. Well, we already know that from here, so this provides no additional information. The origin is both an x and a y-intercept. So we only have one point on the graph so far. Okay, let's attempt to get vertical asymptotes then. No simplification here can be done, so we'll attempt to then find where the denominator is equal to 0, and that's not going to happen. X squared equals negative 2. No number squared can be negative in the real number system, so we have none. No vertical asymptotes. So we have 1 point so far, and that's it. But we have horizontal asymptotes as well. So let's do horizontal asymptotes. Horizontal asymptotes. Take the highest degree term, top and bottom. See, function is higher degree in the top than the bottom, so when you divide it, you get x squared. And of course, as x gets really, really large, the y-coordinates are going to blow up. In other words, in the recipe there in the PowerPoint slide, if the top degree is larger than the bottom, then you have no horizontal asymptotes. So all this work, and we've learned only that there's 1 point on the graph of the function. What can we do? Well, we could attempt to look at symmetry. See, now I'm going to go to symmetry because I don't have anything to work with. So let's replace x with negative x and see what happens. Negative x to the fourth divided by negative x to the second plus 2. Well, this is an even power, so that will take the negative sign right out. And this is to an even power, so that takes it right back out. So what you end up with is the original function. Ha! I guess I don't mean horizontal asymptote. I mean, ha! We have y-axis symmetry. Because replacing x by minus x produces the same thing back. Well, if we have y-axis symmetry, then we can't have origin symmetry. Circles have both, but this is not a circle. Okay, now what? We've exhausted everything. Well, there's point plotting. We can do that. So there's a y-axis, and there's an x-axis, and we can think about plotting some points. We have one right there. And we know that it's symmetric, so whatever's on this side is the same as what's on this side. So let's plot some points. Okay, let's say when x is equal to 1, what happens? We get 1 to the fourth is 1, divided by 1 square is 1 plus 2. We get a third. Okay, so 1 gives us a third. 2 points. Oh, we have symmetry, so negative 1 would also give us a third. See, that's why I said, ha! That's an important revelation. So this is the same thing as f of negative 1, because we have symmetry. In a similar way, f of negative 2 would be the same as f of positive 2. Let's find out what that is. 2 to the fourth power, 2 times 2 is 4, times 2 is 8, times 2 is 16, divided by 2 square, plus 2. So that's 16 divided by 6. That would be 8 thirds. Okay, well that's almost 3. So we move over a little bit more here to x equals 2, and we're moving up now to 8 thirds. Same thing on the other side. Curious. Beginning to look more and more like a parabola. In fact, yes, if you continue to plot several more points, you will find that this looks a lot, it is not, but it certainly looks a lot like a parabola. In fact, it looks a lot like y equal x squared. It's not y equal x squared. It's a rational function. Like I said, they come in a variety of flavors. Okay, let's see what else we have to do. Ooh. Find slant asymptote for this function. Okay. You define a slant asymptote. Under what condition do you have a slant asymptote? So if numerator p of x is exactly one more than the denominator q of x. Exactly one more and only one more. Is that what we have? We have 2x squared minus 5x plus 7 divided by x minus 2. Yes, we have exactly one more. Then slant asymptote exists. Okay, so we have that because we have our function to be 2x squared minus 5x plus 7 divided by x minus 2. Okay, exactly one higher degree on the top, right? This is p of x, than the bottom. That's q of x. Okay, how do we find it? We find it by polynomial division, or synthetic division if you know that. So we'll take the polynomial in the numerator, 2x squared minus 5x plus 7, and we'll divide it by the denominator, x minus 2. So let's see what we get here. 2x. If you don't know polynomial division, I suggest you go back in the book and take a look at that. So this will be 2x squared minus 4x. Okay, then we got to subtract. Subtract, that's 0. That becomes positive 4x. So then we get a minus x there. Bring down the 7. Okay. And then here we'll have a minus 1. So that'll give us negative x plus 2. Then we have to subtract that. That'll be a negative 2. And 7 negative 2, that's a 5. So that's your remainder. Okay, so what we have found is this. The original polynomial f of x, which was written as 2x squared minus 5x plus 7 divided by x minus 2. When we do polynomial division, we end up with 2x minus 1, and then the remainder of 5 divided by the divisor x minus 2. This is exactly the same as this, and it's a very good exercise to take this, get a common denominator, and show it goes back to here to check the result. It's a very good exercise. This part right here, this is the equation of the slant asymptote. So that means y equals 2x minus 1. Okay. What is a slant asymptote? Okay. Well, very quickly here, I'm looking at the original function, and x cannot be 2. Now, I have taken the time to consider factoring the top and removing common factors, and it doesn't happen. So x equals 2 is where the denominator is not defined. So we make a small picture over here, y-axis, x-axis. X can't be 2, so there is a vertical asymptote right there. Function cannot cross the vertical asymptote, so we'll label that as VA. Now we have a slant asymptote, y equals 2x minus 1, straight line. Y-intercept negative 1, slope 2. So that comes up roughly like that, say. There's your slant asymptote. So that is y equals 2x minus 1. And the graph of the rational function is trapped between the slant asymptote and the vertical asymptote. And let's see if you do a little bit of work here. It'll be in here. There and in here. Very good exercise to show why that's the case. It's going to take some point plotting. Also, you could look at the x-intercept and the y-intercept. My picture could be off a little bit. I'm doing this very quickly. But what I'm trying to show is what is a slant asymptote. So the graph may or may not be fully accurate, but the slant asymptote, this is a linear function, means that the function will have its normal behavior near a vertical asymptote, but near the slant asymptote, it takes on the characteristics. It almost becomes perfectly straight as it approaches that slant asymptote. And it does so here as well. A very curious feature of rational functions. They're tough to frame in a box. They don't all belong in the same box. Let's see what else we have remaining to do. 6. Problem 7. Okay, here we have an application problem. Let's take a look at that. Company is planning to manufacture wheelchairs. The cost C in dollars of producing X wheelchairs is given by the function 500,000 plus 400x. Okay. Doesn't say how often we are producing the wheelchairs, so let's say it's on a per month basis. So this is the cost, probably in dollars. Yes, cost in dollars of producing X wheelchairs, we'll say per month. And that's the function that will give you the cost. Okay? Write the average cost function. Okay, well, the average cost function is symbolized with a C bar. C bar means average cost. So this is average cost, C bar. And that's given to be the function divided by, so here's the function, divide by x. Well, why would you just take the function and divide it by x? Well, because the average cost, this is the cost per wheelchair. The cost per wheelchair. And look back into the problem, we're producing X wheelchairs. So you take the cost, which is C of X right here, and divide it by X, which is the number of wheelchairs, and then you have the cost per wheelchair, and that is definition of average cost. Okay, what else do we need to do? Find and interpret C bar of 1,000 and C bar of 10,000. Okay, 1,000. So this is finding the y coordinate, but it's in application, so we'll have to consider what that means. So 500,000 plus 400 times 1,000 divided by 1,000. So 500,000, this would be 400,000, that's 900,000 divided by 1,000. So that makes 900 as the result. Okay, what is this saying? It says that when 1,000 chairs are produced, the average cost is $900. If you go back to the original function and ask what's the cost for not producing any wheelchairs, well, that would be when x is equal to 0 and the cost is 500,000, $500,000. So if we now have a production level of 1,000 wheelchairs, it brings down that cost to $900 for each wheelchair. Okay. Typical with businesses, you mass produce so that the more production level you have, the less it costs for that particular item, which is why certain big name stores can always offer lower prices. Let's repeat the exercise for 10,000. So that would be 500,000 plus 400 times 10,000 divided by 10,000. Okay, so this would be 4,500,000. 4,500,000 divided by 10,000. Okay, so when you 1, 2, 3, 4 take away 4 zeros, you have 450 remaining. So we end up with 450. So now, at a much higher production level, 10,000, the cost per wheelchair that was $900 is now reduced to $450. And that's what I meant by mass production yields lower costs to the consumer. The last question up here is, what is the horizontal asymptote for the average cost function, and describe what this means for the company? Okay, so we have to look at our function here, and it says average cost function, so this one right here. And we have scan the numerator, scan the denominator, take the highest degree terms, and divide them. So 400x divided by x. So we'll come down here, looking for horizontal asymptote. Highest degree term in the top, highest degree term in the bottom, yields 400. So that's your horizontal asymptote. Y equals 400. So what does that mean? Well, think about this in the graphical context. You have the cost here, and then you've got X, which is the number of wheelchairs that you're producing. And the cost is being reduced, 900 down to 450. And if you produce, well, this here means as the number of wheelchairs produced becomes substantially large, the average cost approaches $400. That's your horizontal asymptote. So here at 400, we have a low range. And the function will be approaching that, but we know it approaches it from above because the cost is dropping. So the cost function looks like that. And as x becomes larger and larger and larger, the cost becomes lower and lower and lower. So you could say that this is the lowest possible cost in dollars for producing virtually an unlimited number of wheelchairs, or perhaps for millions. Or you could simply say that as the production level increases, the average cost approaches that value of $400 per wheelchair. So the more you can produce, the cheaper you can sell it to the consumer. Let's see if there's a problem 8. Nope. That concludes section 3.5 problems.